we're gonna talk about integral domain. Suppose you want to solve the equation x squared minus 4 equal to 0. In regular algebra, you would factor the left-hand side, giving you x minus 2 times x plus 2 equal to 0. Here, the product of two terms is 0, so one of the terms must be 0. If x minus 2 equal to 0, then x equal to 2, and if x plus 2 equal to 0, then x equal to minus 2. So this equation has two solutions, 2 and minus 2. This seems straightforward, but to solve this equation, we use a big assumption that if the product of two terms is 0, then one of the terms must be 0. In abstract algebra, this is not always true. Let's see an example where this technique of solving equation does not work. We will solve the equation x squared plus 5x plus 6 equal to 0. In the integer mod 12, if you factor the left-hand side, you get x plus 2 times x plus 3 is congruent to 0 mod 12. If you set each term to 0 mod 12, you get x equal to 10 or x equal to 9. Since there are only 12 numbers in the ring of integer mod 12, let's go ahead and check all possibilities. We will plug in 0 through 11 into the polynomial x squared plus 5x plus 6 and see what we get. If you plug in 0, you get 6. So x equal to 0 is not a solution. If you plug in 1, you get 12, which is congruent to 0 mod 12. So 1 is a solution. Here is a solution to the equation that we did not find by factoring. Plugging in 2 gives us 8, 3 gives you 6. And let's quickly fill out the table for the remaining numbers. We see this equation has not true, but 4 solutions, 1, 6, 9, and 10. Factoring only identify the solution 9 and 10. To see the problem, let's take a closer look at the equation. After factoring, we have x plus 2 times x plus 3 is congruent to 0 mod 12. Setting each term to 0 gave us 2 of the solutions, 9 and 10. But why did we miss the other 2? To see why, look what happened. When we plug in 1, this gives you 3 times 4, which is 0 mod 12, and you plug in 6. You get 8 times 9, which is also 0 mod 12. We now see the culprit, working mod 12. It is possible to multiply two non-zero numbers together and get 0. We say the integer mod 12 have 0 divisor and it is the 0 zero divisor which make solving solution more difficult with real and complex number. This does not happen. These fields do not have zero divisor. Zero divisor. This name was chosen because division can be defined in terms of multiplication. For example, when working with integer, we say b divide a if b times c equal to a. For some c, from this definition, the term zero divisor makes sense. In the integer mod 12, 3 times 4 equal to 0. So both 3 and 4 divided 0. They really are zero divisor. Except this time, we will work mod 11 instead of mod 12. The integer mod 11 do not have any zero divisor. This is because 11 is prime number. The only way the product of two numbers is a multiple of 11 is if one of the numbers is divisible by 11 and none of the integer 1 through 10 is a multiple of 11. So this string does not have any zero divisor. Like before, we can factor the left-hand side, giving us x plus 2 times x plus 3, congruent 0 mod 11. Setting each term to 0 gives us x equal to 9 and x equal to 8. Let's see if there are any other solution by packing in order integer and 11. When x equal to 0, x power 2 plus 5x plus 6 is equal to 6. Packing in x equal to 1 gives us 1. X equal to 2 gives us 9. Let's go ahead and fill out the rest of the table. We see that the only solutions are 8 and 9. The two solutions we found by factoring. When R does not have any zero divisor, the traditional technique of solving an equation by factoring and setting the terms to 0 does work. For this lesson, there is a term for such links: integral domains.
Here is the complete definition. An integral domain is a commutative ring R with a multiplicative identity 1 and no zero divisors. Why are integral domains commutative? After all, it seems that the most important thing, at least for solving equations, is there are no zero divisors. One reason is when the idea of an identical domain was developed, much of the focus was on generalizing the integer for using number theory. Here, the word integral in integral domain is a non-commutative ring R with zero divisor is a domain. That is, however, a term for an arbitrary ring with no zero divisor, a domain, but you will encounter integral domain more frequently. Integral domains have another useful property, the cancellation property. Suppose you want to find the solution to equation 2x equal to 6y. Your instinct might be to first simplify this by dividing both sides by 2, giving you x equal to 2y. But working with a ring, you may not be able to divide, so different approach would be to factor both sides, then cancel the 2s, giving you x equal to 3y.
Factoring and cancelling does not require division, but can you safely cancel in any ring? Unfortunately, look at the equation 3x equal to 6y in the ring of integral mod 12. This equation has multiple, but one solution is x equal to 6 and y equal to 1. This is because 12 is congruent to 6 mod 12. But look what happens if you factor out 3 then cancel. We get x equal to 2y. Now if you plug in x equal to 6 and y equal to 1, you get 6 is congruent to 2 mod 12, which is 4. So in the original, 6 and 1 is a solution, but after cancelling, it is not. Cancellation property. To find out, suppose a times x equal to a times y is some ring R and a is not 0. If we get everything on one side, we can factor out a using the distributive property. If the ring R does not have any 0 divisor, then we know that x minus y must be 0 because a is not 0. And this implies that x equal to y. In other words, we can cancel a from both sides. So another benefit of an integer domain is the cancellation property. To recap, an integer domain is a commutative ring with one that has no 0 divisor. The absence of 0 divisor means you can use the cancellation property. It also means you can solve an equation by factoring and setting the term of 0.
Thank you for your attention, and we hope that this video is useful.